All right, now we'll come to stability. So an object will stably return to its base of support given some simple rules. First, we're dealing with gravitational torques. And when you're dealing with gravitational torques, you need to know where to apply them. You have two potential pivots, in this case here or here. And an object's center of gravity simply describes the singular position where the force of weight can be applied for the purpose of calculating a torque when you have an extended object. So long as the center of gravity remains between your two bases, your two contacts that make the base of support. So there's some basically the distance here that describes your base of support. So long as the center of gravity is between those 2 points, you will return back to your original base of support. That means that if you start to rotate this angle, this object some angle off the ground, there will become a critical angle when the center of gravity is directly over one of the 2 points of contact that make the base of support. That's the critical angle. If you go beyond that critical angle, then the object will return to a different base of support. And if you stay below that critical angle, you return back to your original base of support. Finally, the robust definition then for an extended object. This is somewhat unrelated to this base of support business, but if I have an object and it's currently at rest, then the condition for static equilibrium is not just that tau net be equal to 0, but of course we still need F net to be equal to 0, which we can partition into two components of F net. And so if you know an object is at rest, which you do in a lot of your homework problems, you can leverage these three different things to help solve a problem. One other thing that can be helpful in solving problems that involve torque is, since one of your conditions is that tau net equals 0, it's important to realize that if we go back to our bolt example, it doesn't matter if there's a natural pivot, like here the center of the bolt is a natural pivot. For the purposes of calculating tau net, it does not matter where you place your pivot. So if you know there's forces somewhere and you don't know the size of forces somewhere else, like let's say I didn't know the force here, but I knew some forces down here or something, I can decide that for the purposes of calculating my torque, I'm going to place the pivot here where I don't know the force. Well, then necessarily, since torque is equal to RF sine theta, anytime I place a force at a pivot, the radial distance goes to 0, and that does not contribute to my net torque calculation. So it always allows me to remove one of the forces from the torque calculation so that I could solve for the other ones. That's a very useful problem-solving skill when you have objects, extended objects in static equilibrium.